say you have an analytic function, that obviously means that you can calculate its derivative. Now, if you're interested in the magnitude squared of that derivative, it actually turns out that this is equal to the determinant of this Jacobian matrix over here. I'm sure you didn't see that coming. However, it's rather straightforward to show, so just pause the video and try to convince yourself of that fact. We start from the fact that our function has a derivative, and we know from the textbook that in that case we can also write that the derivative df dz can be constructed by taking the partial derivative of u with respect to x plus j, the partial derivative of v with respect to x. This is a complex number with a real part and an imaginary part. So if you're interested in the magnitude squared of that derivative, then you just square the real part and do the same with the imaginary parts. So du dx squared plus the v dx squared. And then we'd like to show that this is equal to the determinant of that Jacobian matrix. So let's bring back our Jacobian matrix and let's calculate the determinant. So this times this minus that times that. So we get the u dx dv dy minus the v dx du dy. Question: are these two expressions the same? Let's first focus on the first terms here of these two equations. Now, what they have in common is this du dx. However, there's also a second factor. In order for these first two terms here to be the same, this means that this second du dx should be equal to dv dy. So we need to have that du dx is actually equal to dv, I'm not so happy with my handwriting here, dv dy. Let's take a look at the second terms over here. And again, what they have in common is a dv dx. So we need to have that this second dv dx here should be equal to minus du dy. So we should have that dv dx should be equal to minus du dy. And if we take a look at these expressions over here, we know that these are true for holomorphic functions because they are exactly the Cauchy-Riemann conditions, which we know are fulfilled. So indeed, we have shown that these two expressions are indeed the same.